Okay, I wanted to finish talking about this lab so that you won't get stuck trying to write it up. So in class today we were making the graph. We had decided you were going to go up by every 2 blocks on one side. Okay, and so 1, 2, 3 every 2 blocks apart. And across the bottom by like 0.1s by 4. So this is really 10 centimeters right here. So this would be 5 centimeters just to help you, right? 15, 20, 25, 30, 35, 40 centimeters, or 0.1, 0.2, 0.3. And then you're going to plot your numbers. So your FG, your first one, is like 1.962, and you need to look at your X, and I don't have your data in front of me. Maybe your X is like 5 centimeters, so then you would go up, and you would almost be at 2. There's a decimal in there. I don't know if you can see it, but would almost be at 2. 1.962 is pretty close to 2. And then the next one is 400, so it would be 3.9, so it would be pretty close to 4. So you find how much it was stretched, and again, I don't know what that is. So I'm just going to make, and it's really close to 4, so I'm going to put a little dot here. And then the next one was 6, so times 2, that's 8, divided by 4 times 3. So it should be 5.866, so not quite 6. And again, you're going to keep going, so I don't know what that's, I'm really making these up here. So it's almost 6, so, but not quite. It's maybe just over the, like the middle one would be 5.5, so maybe halfway through the next block. And you keep going with all your dots. Then you take your ruler, and I'd said this in 4th period, but not in 2nd. In theory, we would probably want it to go through the origin. In real life, it's probably not going to, because we could hang 100 or 200, 100 or a 50 gram weight on that spring, and it wouldn't stretch it. So it's not probably gonna, to get your best fit line, you don't really have to put it through the origin. I'm just going to turn my box around here to see if I can support this. Just hang on a sec. I just want to draw a line here. Okay, so you're going to draw your best fit line through all your points. I cheated and didn't draw all my points, but you're not going to do that. You are going to draw all your points and then put your best fit line. And it might not go through the origin, and that's all right. Okay? So that's number 7. So number 8 says, using your graph, calculate the spring constant. And we talked about that today. The equation of a line is y equals mx plus b. And you might have a b on because this spring's kind of heavy. So y is f and x is x. So that means m must be k. So really, you're going to find your k by doing the slope. So remember, m is y2 minus y1 over x2 minus x1. So when you do this, you want to look at your line and you want to find like 2 points on the line that actually cross through the corners, right? So you might pick like these two. And this one looks like it's 8.5, and it looks like it's 2 point, okay, so it's 2 point, oh wait, I lost it. It's 0.275, 0.275 meters, and it's 7.5 newtons. And then I forget, I think I picked this one up here, and it's 12 newtons. Your line will be longer, because you should have another one, and it's 4.5, so it'll be 0.45 meters and 12 newtons. And so then starting with your y, for me it would be 12 newtons minus 7.5 newtons, and then divide it. I started with the 12, so I had to start with the 4.5 minus the 0.275. Do not leave this in a fraction. Our spring constants are never fractions, right? So to do the top, do the bottom, get a number, not a fraction. I know in math you do leave your slopes in fractions, but this is a spring constant, okay? So we want a number here. All right, so that is number 9. Number 10 says, determine the value of the unknown mass. So now you look at your chart, which I don't have filled out because I didn't do the experiment. But you have a delta x for your unknown mass. So and it's probably somewhere around like it's like 2.6 centimeters. So that would be somewhere down here. So whatever that number is, and I'm using the curly graph paper, you're going to find it on your graph, and you're going to take your ruler, and you're very carefully going to make a line up to the spot where it hits the graph, and then you're going to draw a line over, again with the ruler, and you're going to read this point off the graph. And when you read this point off the graph, that's going to be the FG of your unknown. And so you need to read it as carefully as possible. That's why I wanted you to have a long, a big spread out graph here. And once you have that FG, then your M is just going to be FG divided by G. Okay, so that's how you get it off the graph. That is for number 9. Then number 10 says calculate the percentage error. So you already weighed your actual unknown, and so then it'll be the weight that you weighed it, so the actual, minus the one you just found on the graph, divided by the actual times 100. Okay? So whatever you got on the scale is your actual, and whatever you get when you read it off here and divide by 9.81 is your graph one. So that's for number 10. So number 11, 12, and 13 are the ones that we didn't really get to. So 11 says, use the value that you found for the spring constant, calculate the elastic potential energy stored in the spring when the extension is 0.2 meters. So I'm just going to do it up here. So it's asking you to find EE, which of course is equal to 1/2 kx squared. And you found your k. It was right down here, whatever you got for your slope. So they want you to use that for k. And they're telling you to use x as 0.2 of a meter. So x equals 0.2 meters. So they want you to find EE, okay, to calculate it. That's for number 11. Number 12 says you can find the work done, which would be the change in elastic potential energy in this case, by finding the area under the curve, which we were doing earlier today. Read the appropriate values from your graph and show your calculations for work done on the spring as stretched from 0 to 0.2. So 0.2 meters is here. So you're going to find this area. Now if you don't go through 0, you're going to need to divide it into a triangle and a rectangle and find the two areas. So find the area of the triangle and find the area of the rectangle. If you do go through the origin, then it's only going to be one. Okay, so find them and add them together if it's two areas. And that is the work done according to the graph, right? Area under the curve. And then 13 says that if you've done 6 to 12 correctly, the answer to 11 and 12 should be close. This is expected since the work done should be, by the mass, the area under the graph, should be equal to the increase in potential energy. So are they? So is what you got for number 11 up here equal to the total area that you found down here? If you did a good experiment and you had your dots were lining up and you did a good job finding your best fit line, then the answer to number 11 and the answer to number 12, which is the total area in the first 0.2 meters, should be the same. So question 13 says, are they? And if they aren't, you might, want to suggest a reason or two, okay, of why they aren't. And then that's all the calculations for the graph, okay? So then what else do I want you to do? I want you to write me a conclusion. Talk about what you found for the unknown mass compared to what it really was and how your percentage error was. Talk about your slope, and talk about how good you were at getting your spring constant, the slope, and that'll be determined by how close 11 and 12 are. Okay, remember you made a prediction for me about the spring constant and the unknown mass, so don't forget to mention what you had predicted and what they were, okay, and how good you were or how far off you were. All right, and that will be it then for the lab. You'll hand in the chart, the answers to the questions from 6 all the way down to 13, and the conclusion. Okay? So really the only thing you have to type up is probably the conclusion.